Let us discuss a question from strength of materials. So this is basically what is asked is the bending moment diagram. If we have a moment M acting at a point B, so this is a simply supported beam. Let's first get the reactions at C. So at C you have a roller, so let's put R1 here and R2 here and a moment at this point. So when you balance first the force balance, there is no force, external force, so R1 plus R2 is 0. Remember it's a hinge reaction, but this horizontal, at this point there has to be two reactions, R2, and there has to be some horizontal reaction, but that is 0 because there is no horizontal force. Now we need to find out R1. So if we take a moment, this summation of forces is equal to 0 for the entire beam. And now if you take about A, summation of moment about A has to be 0. So that if you take, so moment M, because of M it is M, because of R1 it's R1 into total length L is equal to 0. Okay, so let me write here. So R1 is M by L upwards, and therefore R2 from the first equation will be minus M by L. So basically R2 acts in a downward direction on the beam at A. So you got R1, R2. Now let's draw the bending moment starting from towards right. So let's take a section here between B and C. So when you take a section here between B and C, okay, at this the reactions R by L and this is X. So the moment, the bending moment at this point will be R by L into X, right? And what is R? M by L. Right, sorry, this is not R, this is actually R, so this is M by L only. So let me write R1. So that is the bending moment at this section between B and C, it's R1 into X, and that is nothing but M by L X. And so you can see as X varies from 0 to till point B, which is L by 4, this is let's say B, the bending moment varies linearly. And now the sign. Now remember that this is the bending moment that is produced by R. Is R produces anti-clockwise movement. So the reaction moment is nothing but the bending moment. Okay, the internal reaction at that cross section, internal reaction of the beam at that cross section, that is called as bending moment. So this will be clockwise because R produces anti-clockwise R1 into X. So now this is a sagging moment. Sagging is something like a simply supported beam. This is called sagging when you have a bending moment like this at an element. Okay, and that is the case here. If you take a small element at this cross section, the bending moment is like this. So it's a sagging bending moment, is positive, we draw it above the axis, and so it varies from 0 at C, and at B it is L by 4. So it is M by 4 at B and positive. So and it's linear because it depends on X and it's a straight line, it's a linear. So out of all these options, if you look, this is wrong because it has to be drawn upwards between B and C. It's also wrong, so only C is the right option. But we also look at, just to confirm, we also look at the other part. Remember that C and D are almost similar, but only thing is that BC has to be drawn upward. That's why it's mentioned that sagging bending moment is positive. So that line is very important. Otherwise, going by the quantities, C and D has the same bending moment at each cross section. Okay, so now let's see what happens if I take a section just to the left of B. So this is point B where the moment M is applied, and this is M by L. Now if I take a section just to the left of B, the bending moment here is nothing but just to the left of B. Okay, even this axis doesn't. So then M is clockwise, M by L into L by 4 is anti-clockwise, but M is clockwise, so M minus, so it is basically 3M by 4, and that is clockwise. So the direction is changed here, right? So this effectively is clockwise, so the reaction has to be in this way. The reaction just to the left, reaction of the beam just to the left of B has to be in this way. and so it has changed to 3m/4. That's why minus, because initially when we took like this it was positive and it was m/4. Also here the direction got changed, or if you want to consider this in this way, it is minus 3m/4. Okay, so 3m/4, because of the concentrated load there's a change in the shear force diagram. Because of the concentrated movement there's a change in the bending moment diagram. That's why it has changed from m/4 and minus m, so it becomes 3/4m. And going beyond that, at A the bending moment has to be 0 because it's a hinge, it doesn't support any movement, it has to be 0. And because of and it has to be a straight line from 3/4 minus 3/4m, it has to go to 0, has to be a straight line. So C is correct. Okay, so always when you are given with the bending moment diagram and you are asked to find out the appropriate bending moment diagram, you have to remember one thing: get the reactions first, and then if it is a concentrated load, the bending moment diagram you will see a straight lines in bending moment diagram and triangular like kind of structure. So that is because of the concentrated load, and because of concentrated movement there will be a sudden change in the bending moment that we have seen at point P. So all these facts you have to remember, and more or less all these facts you can get from taking a section. So what we do is we start from the right, we took a section between B and C and then found out the equation mx/L, and from that it is clear that it's a straight line, 0 at C and m/4 at B. Then just take a section just towards of B, left of B, and the bending moment drops suddenly to minus 3/4m because of the clockwise movement m, and then it has to go to 0 at A, so you can just join. Okay, so C is the answer. Thank you.